have now determined that biasing the transistor at a constant drain current is better than biasing a transistor at a constant VGS. That is, the sensitivity of the transconductance GM to variations in transistor parameters such as the current factor and threshold voltage will be much smaller if you maintain the same current through a transistor as opposed to maintaining the same gate source voltage. Okay. That is, the context is the following. There is some nominal threshold voltage and nominal current factor, let us say 1 volt and 100 microampere per volt square. But these quantities vary with temperature for a given transistor, and also they vary from transistor to transistor. So, every piece that you make with a different transistor will have a different gain, and also it will have different gain at different temperatures. We would like to keep these specifications as tightly controlled as possible. So, this means that our original idea was to make a common source amplifier where every common source amplifier you make, which is basically copies of the same design, should have a VGS of 3 volts. Now, we know that that is not a good idea. What is a better idea is to somehow make sure that in every amplifier that you make, the transistor carries a current of 200 microamperes. Okay. Now, how do we go about doing this? It is not as easy as it sounds, as we will just see. Okay. This is correct, but how do we do this? The point is that the transistor is a unilateral device. Okay. This, by the way, is true of all the control sources and so on. What does it really mean? For now, let us ignore the slight dependence of drain current on the drain source voltage. Okay. So, we can safely say that ID depends only on the gate source voltage. Okay. That means that if you apply some gate source voltage, and of course, we will assume that VDS is more than VGS minus VT, so that this approximation is correct. If you apply a certain VGS, you will get a certain current. Okay. But you can't apply a certain current and expect that VGS will be magically formed. Okay. Now, every control source is of the same type. So, let us take a voltage controlled voltage source. This is also a unilateral device. This means that, so let us say this is K times Vi. If you apply 1 volts here, here you will get K volts. Okay. But you can't apply K volts to this side. This circuit has no meaning. You can't apply K volts and expect 1 volt on the other side. So, that is the meaning of a unilateral device. Okay. So, if you have a 2-port network, if let us say Y12 is 0, that becomes a unilateral device. That is, you apply something to port 1, you will get something at port 2, but you can't apply something to port 2 and expect something at port 1. Okay. So, this is a unilateral device. This is as opposed to, let us say, a resistor. Okay. This is an important difference. So, a resistor follows V equals IR, and I could always write this as I equals V by R. Now, this is just mathematical relationship, but it also works this way. That is, if you apply a current I, you can force it through a resistor, and the voltage that will be formed will be equal to I times R. Alternatively, you could also apply a voltage, and the current that flows will be equal to V by R. Now, a MOS transistor is not like that. Okay. So, ID is current factor Kn times VGS minus VT squared. I can of course invert this mathematical relationship. I could say VGS is VT plus square root of 2ID by Kn. Okay. This is possible, but whereas I can do this, I can apply VGS and this ID will flow. Okay. Okay, this will work, and this is just to make sure that the transistor remains in saturation. You need some bias. On the other hand, you can't do the other way around. Okay, the converse, though you can calculate it, you can calculate VGS from the current or current from VGS. You can't apply some ID here and expect that this VGS will appear there. It won't work at all. Okay, if you do in fact make this circuit, what happens is the drain source voltage will reach some very high values and the device will go out of its limits where this model is valid. Okay, something else will happen. Okay, either the device could be damaged or the current will be flowing into some other junctions in the device and so on. So this doesn't work at all. Exactly like a control source where control flows only in one direction. Okay, so this is a very, very important thing to remember. Although you can invert the mathematical relationships, you can't arrange a circuit in the converse direction. Okay, VGS is the controlling quantity and ID is the controlled quantity. The other way around doesn't work. So how do we set up a transistor so that a fixed amount of current is flowing? There is only one way. There is only one quantity that changes the current in a MOS transistor, and that is the gate source voltage. So what you have to do is the following. Okay, let's say you are doing this manually. You have an ammeter here and you apply some bias VDS which is more than VGS minus VT, and this is not difficult to arrange. If you choose a sufficiently high value here, it will remain in saturation. Then I need to connect a voltage source to this VGS. I have to keep on varying this. Okay, so I vary it, I look at the ammeter reading, then let's say it is 50 microamperes. Then I know that I want to have a current of 200 microamperes. So what do I need to do? If it's 50 microamperes, I know that I have to increase VGS to increase the current. So I increase VGS a little further, maybe it becomes 100, then I increase it further, it becomes 150 and so on, and I increase it finally until it reaches 200 and then I stop there. Okay, so that will work. It could be that I started off with a very large value of VGS, I don't know what to apply, and the current is already 400 microamperes. Oh, I know that the current is more than what I want, which is 200 microamperes. So I have to go on reducing VGS until this current becomes equal to the current that I want. Okay. So in other words, I have to observe the actual drain current. I have to compare it to the desired drain current, and in this example this is 200 microamperes, and based on whether the actual drain current is less than or more than the desired drain current, I have to increase or decrease VGS as required. Okay. So in other words, I have to look at the output, which is the drain current, and control the input, and I have to do it in such a way that the error between the actual drain current or the actual value and the desired value becomes smaller and smaller. Okay. In other words, this whole process is known as negative feedback, and this is what I need to use. Okay. So the way to set a fixed drain current is through negative feedback, because it's only by changing VGS that you can control the drain current. You can't apply the current directly to the drain of a transistor and expect that current to flow. Okay, the transistor will not be operating in the correct region of operation. The way to do it is to compare the actual drain current to the desired drain current and continuously adjust VGS such that the error between the desired and actual values goes to 0. In other words, we have to use negative feedback. Okay, and there are a number of schemes with which you can do this, and you will quickly see that the number of biasing arrangements are really, there are lots of them. Okay, what is more important is to understand the principles behind them and not learn individual topologies by heart. Okay, so you need to know the simple topologies, but the principles are more important. Okay, so we will discuss all these arrangements in the forthcoming lesson.